Do you guys hear me? All right. So I'm just going to start. As you know this, and you probably know about this before, Joe's not here today. There's a pretty good chance none of the material is going to be on your exams. But they're actually pretty easy. So let me... All right, I'm just going to hold it. So I'm going to give sort of a guest lecture today on big data analytics systems. And so about myself first, I was actually doing my PhD at Berkeley in the UC Berkeley AMP Lab on the fourth floor of Soda Hall. And I started taking my leave about 2 years ago to start Databricks with a bunch of other folks from Berkeley here. So I'm now sort of a co-founder and architect at Databricks, working on Spark and our proprietary sort of data platform offering. And last piece, I'm actually going to come back to this, which we actually had an effort that I led last year that break the previous world record on how fast you can store the 100 terabyte. I'll cover that later. And as you notice, the talk today actually had it in the title Analytics. And so just to start, I want to sort of define what we meant there. One is this sort of historically in databases, this sort of separation between what you would call transactional workflow and analytics. And transactional workflow, sometimes you hear the term OLTP. How many of you have heard of that term? Sure. A few of you. So there's OLTP, which pretty much means transaction processing. Or sometimes you might hear the word online. What it really means is this is a database to serve your transactions, like a lot of point lookups and updates. For example, every time you visit a page and buy something, you might actually update the database then to record that transaction. And the other part, which is what we're going to be focusing on today, is analytics. And what analytics mean is essentially you're trying to run some query that might touch a lot of your data. From the workload point of view, touch a lot of data to compute some metrics, compute some KPI or some reports, and use that report sort of to drive your business decisions. And a very sort of simple analytic query is like, for example, just grouping by the store and then compute how what's my revenue this year for each of the store. So you might scan every single transaction to compute the revenue. So the big difference is on the transactional processing side, you care much more about just looking up data, maybe individually, one or two or just a few records. And on the analytics side, you might be scanning a huge amount of data. So for the rest of the talk, I'll be sort of talking about what is big data and cover some of the more common technology stacks that's being in use today. And as I learned, you guys have already sort of used Spark in one of your assignments. So I'm going to assume you're all Spark experts by now. And at the end, I want to come back and sort of talk about, so what's really different between this sort of whole new hype, big data, and what you've been learning about databases. So it's kind of funny, because big data is basically, you can shorten it to BD, and databases, I'm going to use DB, not to confuse you with Databricks. And one assumption I'm making here, which might not be the best assumption, is I'm going to assume you roughly have some idea about how a lot of the things you have learned in this class can be applied to a parallel setting. So I've heard that Joe occasionally put in sort of a slide here or there about how maybe you can parallelize a specific algorithm. Like, for example, how do you use joins in parallel? I'm going to assume you have some context about it. So as I was preparing slides, I went up to Google and did a search on the Google trend for big data. And big data is basically taking off. There's a lot of hype. You can see it's almost like a hockey stick growth up until maybe 2004. And then start taper a little bit off. And one funny thing was I was contrasting with small data. It turned out before 2011, people care as much about small data as big data. But now all everybody's talking about is big data. So that brings me to the question, what is big data? So anybody? What do you think big data means? And don't give me the awkward silence. What's the first word in big data? All right, it's big. So this big data means it's really big. So again, just like every single other hyper-hyped word or terminology in technology, there's actually no very good definition of big data. Different people, depending on who you talk to, you might actually get different definition of it. One sort of more commonly accepted definition is by this company called Gartner. So what they do is they essentially the leading technology analyst firm. They basically analyze technology and make recommendations for like CIOs and all of that. And Gartner's definition of big data is this like whole paragraph. Now, of course, nobody can remember a whole paragraph. So people started taking the 3 most important keywords out of it. It's kind of cool. All the 3 keywords start with the word V. So the 3 keywords are volume, velocity, and variety. So if you sort of try to read more about big data, there's a lot of people that's referring, these are the 3 fundamental properties of big data. Now, the first is actually indeed about the size. So volume is about how big your data is. Big data is probably beyond a kilobyte or megabyte. And the second part is velocity, which is how fast your data is coming in. Like, for example, if your data is static and never changes, maybe it doesn't really matter. It's not going to be very challenging to analyze it because you do it once and forget about it. But if your velocity of data coming in is very high, it's actually much more challenging to react and sort of analyze this data. And the last but not least, I think it's probably the most important one among all of this, is variety. And then I do think this is probably actually the differentiating factor between what it is in 2014 to 2015 versus like 10, 20 years ago. There's a lot more different data sources now that you can actually get data from. And there's different formats, and you also, the kind of analysis you might be running on data is also expanding. In the past, most of what people run is really just a group by and a join to produce some report, right? Yeah, basically, everything you've been learning in this whole class is how to do group by and joins very efficiently. Now, in 2014 and 2015, like companies are increasingly applying to the more sophisticated techniques like machine learning and all of this, applying to their data. So for variety, it is both sort of the format of data and the sources of data that's coming in, and sort of the methods you might apply to that data that's becoming more variable. And now, if you talk to more of a technologist, and you talk to them about big data, often they actually use the word big data to refer to the whole new stack of tools that people are using that's not database systems. For example, HDFS, Hadoop MapReduce, and this like Hive, Pick, and all of that. I'm going to cover some of them in the future, and Spark coming from Berkeley. And it turned out a lot of this, essentially, Spark sort of started independent in a way of Hadoop, but HDFS and Hadoop MapReduce is essentially in the Hadoop project, which I assume you guys are sort of know what it is by now. And they were both based on ideas, actually. They were pioneered by Google from 2 papers, one in 2003 and one in 2004. So Google started pioneering a lot of the ideas that are now open source and used by pretty much every technology company, and which become this big data stack. And one very natural question is, how come Google just didn't use database systems? Like, how come Google didn't use Postgres or MySQL back then? Anybody want to? Yes. They need fault tolerance. Why do they need fault tolerance? I see. Great. So why do they need to run it over a cluster of machines? They're dealing with big data. All right. It's very good. Actually, you could probably produce the whole lecture for me. So it is actually pretty much right. So if you think about the big data, there's volume, velocity, and there's variety. So on the volume and velocity side, essentially the rate of data coming in, the total size of data that you're getting is very big. It's big. And then for the variety part, it is about data sources and the complexity of the analysis you're applying. It's becoming more and more challenging. And just some example, right? I think this is back in 2000, probably mid-2000s, which is almost 10 years ago by now, that at the time, Google's web index, and this includes all the images and basic videos and PDFs you can crawl, is about 10 petabytes. And then at the time, or I think now it's actually much cheaper. You can buy a you can buy a terabyte of disk at less than $50. So it's actually fairly cheap. Like, you could almost, with your internship money, buy enough hard drive to store maybe the web. Maybe I'm off by an order of magnitude, but if you do 10 internships, you can. And so hopefully you don't need to do that. But even with that many, just within a single drive, actually the throughput you can get out of them is fairly low. And let's say you just want to read a terabyte off a single drive at about, if you can sustain about 50 megabytes per second, which is probably pretty good for like very low-end commodity hard drives. For the high end, you can probably get to about 100 megabytes per second. It will take you almost 6 hours to do this. So with the volume of data growing, there's two problems, right? One is, which we just touched upon, it is fairly slow to read all this data. And it's impossible also to just fit this data on a single node. A node you might have like 12 disks at very high density storage nodes. So it's probably up to like 12 terabytes to 24 terabytes range in a single node. And then even if you could store them, it's going to be really slow to read them. And the second part is about databases. Database systems are, or at least back in the days, require you to have very well-defined schema. Like the first thing you learn about MySQL is how do you create a table with 10 maybe different fields, and what are the schema and the data types associated with those fields. And those actually don't fit very well with semi-structured or any unstructured data. For example, you want to store image. MySQL is probably actually not the best thing you want to put your data in. So for these two problems, I think Google was starting to actually explore their own technology stack. And if you really think about it, there's no other way other than to distribute both storage and compute. So back in 2003, Google published I believe it's probably the first and the most influential paper out of Google, the GFS, Google File System. And if you haven't read this paper, I really recommend you to go just read the introduction. It's a fairly interesting and well-written part of the introduction. In the introduction, they make 4 assumptions. The fourth one's not super relevant, so I'm dropping it here. But the three first assumptions, the first one is, at Google scale, component failures are no longer exceptions. They are the norm that happens every day, every hour. And files are huge by the traditional standards. So on your laptop, you might have files that's a single picture. That might be in the hundreds of kilobytes. But when you look at what Google are storing, they're storing the entire web. In order to reduce, and so they might be compacting, for example, a whole website onto a single file, or maybe multiple websites onto a single file. So the size of files are actually much larger than the typical files you store on a normal file system. And the third is files are now mostly immutable, which means when you update, instead of updating the files in place, you actually append data to it, and you don't overwrite existing data. So with the 3 assumptions, they built GFS. And the idea is this 3 assumption actually makes it substantially simpler to build a file system that can sustain very high throughput and sort of failures. And the way they did it is it's actually fairly simple. I bet you guys can all design it if I give you half an hour to think about it. It might be hard to implement it reliably, but the conceptual design is actually fairly simple. The idea is, let's say you have a large file. How are you going to store it? Anybody? How would you store a very large file? Let's say it's bigger than a hard drive. Although in this case, it's not that big.
Then you have either you have pointers from one chunk to the next, or you have some kind of index for it.
Right, but let's say it's even bigger than a single machine. What would you do? Yeah. If you have a 50 terabyte file, how would you store it? So divide it up. Right, so divide it. Very, very simple idea. Divide it. You have a very large file, divide it. Now, right, I'll just hold it. Does this work? Good? All right, cool. So if you have a very large file that can possibly fit on a single node, just divide it onto multiple nodes, right? Now, to go beyond that, maybe you don't want to worry about sort of
only for very large files. You want to choose smaller files and large files consistently. So the way GFS did it is that they essentially divide a file into blocks. And the block is a fixed size unit of storage. So in this case, for example, I think back in the days, the standard block size is 64 megabyte. Now, as the file size is growing, people are actually increasing this block size. I think now in HDFS and all of the open source variants, it's very common to have actually 256 megabyte blocks. And the reason you might want to increase block size is to reduce the amount of metadata you have to track. Like for example, in this case, I have 10 blocks or 100 blocks. But if I increase my block size to 256 megabytes, I will actually have only 25 blocks. So first, you divide just data into blocks. And then you would need to place these blocks in different places. And the way they do it is, by default, you replicate the block 3 times. Basically, each 64 megabyte is replicated 3 times. You write it somewhere, one copy, another place, another copy, and a third. And you do this all over the place. Now, it's actually fairly interesting the way they did this placement. The first copy is essentially returned to the node that was trying to write this data. For example, if I'm on machine A and I need to write block 1, the first copy of block 1 would just go to the local machine. So there's no network traffic in this one. It's very fast to write it. And then in parallel, you're going to replicate the block 1 onto other nodes within your same rack. Essentially, I don't know how much you guys have learned about network topology and all of that, but in data centers, typically have nodes, and nodes get put together into a single rack. On the rack, there's usually a top-of-rack switch that's responsible for the cross-rack communication and all of that. So they did it. The second copy is written essentially to the same rack to increase the network locality, because it's faster to write to other nodes in the same rack than other nodes that's out of a different rack. And the third copy, in order to prevent the top-of-rack switch from failures, you will actually write the third copy somewhere else. So even if you lose the whole rack, you still have at least one copy of the data. So this whole thing was essentially done, a lot of it is actually done for fault tolerance. And the other actually benefit out of the replication is now, let's say you have 2 different programs that are trying to read both block 1 of some file. Now you can actually read them from different places rather than all contending on a single node. And so you would divide sort of a GFS cluster into sort of 2 categories of nodes. One's called data node. Data node is actually the one that's storing the data. So data node manages all the blocks locally. But for each of so data node is essentially storing data. And then for each of the blocks, you have metadata that's actually maintained by this thing called a name node. So data node would talk to name nodes, essentially to tell name nodes, here I've written this block and this is the location. And name nodes, in order to prevent failures, name nodes also have other backup nodes. You might have multiple backup nodes for a name node. So when the main name node actually goes down, you will switch it to a slave copy for sort of looking up all the metadata. And then name node is also responsible for a lot of the coordination. Essentially, for example, you use this mechanism called heartbeat, which is I'm going to send you a message every, say, few seconds. And if I don't hear back, I'm going to consider this data node as dead. And I'll sort of, once I consider one data node as dead, the name node is going to instruct sort of other copies of the data to replicate, re-replicate balance to make sure you always have 3 copies of your data somewhere in your cluster. The most interesting part about GFS is really failures. What Google found back in 2003 at their scale was failures are very common. And there's all kinds of different failures. For example, your disk might fail. A single hard drive's lifespan is actually fairly short. Data might actually return sort of incorrectly from the disk. So you might have like a bit that's corrupted on a disk. And then a whole node might fail with those disks. And the top-of-rack switch, as I said, might fail. Or maybe the whole data center switch backbone could fail. The name node themselves could fail. Sometimes the whole data center could fail. I don't think GFS was done actually to mitigate the last one. If the whole data center goes down, pretty much the Google file system goes down. Although there are newer stuff that try to do cross-data center replication. So you are more, you can actually prevent against, for example, earthquakes. So GFS, in short, if there's only one property you have to remember, it is the fact that they are designed to store very large files, and that's immutable. So it makes it actually easier, and they come up with a design based on this assumption that can achieve a very good scalability, reliability, and availability. Basically, almost anything can fail, and the system will still work. Now, once you have all the data stored in this parallels of GFS, the question is, what do you do with it? How do you run queries or computation on it? And so historically, the way you would do distributed programming is through so what we call RPCs, remote procedure calls, or message parsing, so MPIs. And these two are actually really, really hard to do. And the reason is essentially what you're given is just a bunch of machines with operating systems installed on them. And your US application programmer is going to figure out everything. And this includes, for example, how do I propagate my binary file to each of the nodes? And once I propagate them, how do I decide which part of the node is going to handle what data? And now, at Google scale, failures are fairly often. If every hour you might have something that fails, maybe you actually need to take that into account rather than just every time doing a retry. And even without failures, it is very likely for this thing called stragglers to happen. What stragglers means is really just one node might be slow at some point. And this is not very common when we have a very small number of nodes. But when you have a large number of nodes, it's very likely, for example, maybe a node is running some upgrade process at some point. And that upgrade process is using all the CPUs. Now your application programs slow down because of that. Or maybe the hard drive one of the hard drive is broken, and you're sort of using RAID 0 on it, or some sort of RAID on that hard drive. And because one hard drive is gone, the hard drive throughput is actually much lower now, just from that node. So all kinds of things can make a node becoming slower. And when you're sort of dealing with a large number of machines, you're almost always guaranteed to have some node that's slower. And this actually doesn't even happen at it happens more than sort of common also. If you just launch like maybe 100 machines on EC2 and just run some random benchmark on it, you probably realize maybe one or two machines are actually much slower than the rest of the 99 or 98 machines on EC2. So because of that, I think in practice, except the guys that are doing scientific computing, nobody is actually doing now so network programming using RPCs and MPIs at the application level anymore. So what become, I think, was more dominant nowadays is actually what you call a data parallel model. And what data parallel model does is you provide a more restrictive programming interface. So rather than letting you run arbitrary topology or program or architecture, I'm going to give you a restricted set of programming model. And essentially what that programming model says is, this is some operation I want you to run it on all my data. As a programmer, I don't really care when or where you run it, and I don't even care if you run it twice or three times. But this is an operation. And does this sound familiar to one thing you've been doing? Query optimizer, yes, SQL, right? In SQL, you don't really tell MySQL Postgres, please go fetch using index scan for this data tuple and then pipe it through some like sort-based aggregation or hash-based aggregation. You just tell Postgres, this is my query. The query says, group something by this field and run me some count. So this actually, essentially, this is SQL is essentially a way of doing data parallel models. Now, what Google came up with wasn't exactly SQL. It was MapReduce, as some of you know. So this MapReduce paper was published in 2004. I think by the time it was published, they've been using MapReduce for about 2 years within Google. And so MapReduce essentially became the first real widely used data parallel programming model. And actually, I think back then it was even processing about 20 petabytes of data a day. So that was like a very astonishing number, even I think by nowadays standards. And then later on, MapReduce was popularized by the whole Hadoop sort of ecosystem and open source frameworks. You guys know about this programming model already? Because you learned about Spark. Is there anybody that, do I need to go through it? All right, good. So I'm going to skip the MR model since you already learned Spark. But I'm going to go to the more execution part. So given the map and the reduce, so the very restrictive programming model, there's really only two functions to define map and reduce. The MapReduce framework, the engine itself, can automatically split a big job into multiple smaller tasks. And you send essentially the task to nodes, scheduling for locality. So for example, if you have a task that's reading block 1, the underlying framework will try the best to actually send that task to the node that has block 1, so you can read directly from the block 1 local node rather than reading it through the network. So network is I think back then it's still much slower than disk. And then there's a lot of other things we do. For example, we try to balance, we try to mitigate stragglers. Now, and which brings me to the second part, I think it's the most interesting one, is how does MapReduce sort of handle failures and stragglers? The very simple idea is if a task fails, just rerun it and just read the input again and rerun it somewhere else or maybe on the same machine. Now, this has one assumption in mind, because you can't just always do this, right? Can somebody give me a case where this would not actually work? Corporate science again. Yeah, okay, that's a good. So basically you just can't. Yeah, so you can't. So how would you mitigate that? Let's say if your program is incorrect and it's going to fail deterministically, how would you, if you're designing MapReduce, what would you do?
I think I'd at least set a maximum number of retries.
Yeah, excellent. That's exactly what's done. So you would set a maximum number of retries. After retrying multiple times, if it still fails, you would just tell the user, come on, give me something better. Right. Now, there's more than that also, because let's say if your program is correct, this might still be problematic because maybe your input's not there anymore. For example, if my task is reading block 1 and I just deleted block 1 accidentally, the retry wouldn't be able to read block 1 anymore. So now going back to the assumption we make in GFS, remember, GFS assumes most data are actually immutable, and it's append only, which means if you have a block 1 there, block 1 is most likely never going to change. And so that property actually enables the fact that you can do failure recovery through retries. The second part is if a node fails, rerun a map task, or just a task on some other machines. Now this also depends on another part, which actually tied to the first one, is the result of the task you're getting is actually deterministic. It's not node dependent. And the other part that's very important is if there's side effects to the task, the side effect needs to be idempotent. And what idempotent means is running it multiple times will get you the same side effect. Like for example, deleting a file is idempotent, but appending data to a file is not idempotent. If you append twice, you have the data appearing twice. So for the MapReduce recovery to actually work well, your input needs to be there, needs to be immutable. And the second is your task result, basically what gets returned from a task needs to be deterministic. So if I rerun it, it can't just give me a different result. And last is if it actually does something outside of the system that has side effects, the side effect really needs to be idempotent. And with this two, actually this is a great way to mitigate stragglers, which is if the MapReduce framework finds out one of the tasks is slow, there's many different heuristics you can define slowness. For example, maybe you're launching 1,000 tasks, and one of the task runtime is say 3 standard deviation greater than the median. Then you consider a slow task. And how would you mitigate slow tasks? There's a very easy way. You just launch it on a separate node. Hopefully, the second node is actually much faster than the current node. Now, there are cases where this won't work. Like, for example, if a task is slow because of the data and the processing inherent to that task, just launching another copy is actually not going to solve the problem because you're going to be reading from the same data, and you're going to be running the same computation. Now, that's almost a 10-year research project many different people are trying to solve. So really to summarize MapReduce, essentially by providing a data parallel, a more restrictive programming model, MapReduce simplified cluster computing because basically the lower level framework MapReduce itself will take care of a division of jobs into tasks. It schedules them, even mitigates faults. If there are faults, you relaunch and you should make sure the job can still finish running. And you try to also mitigate stragglers. So if there are nodes that slow, the framework will take care of that problem. And the other thing is compare with SQL. Because MapReduce is more of a general programming framework, it's actually flexible enough to model a lot of workloads. For example, what Google was using MapReduce to actually crawl the web back then, and also building the inverted index, which I believe you guys have learned about, information retrieval. Right. Building the inverted index for the web using MapReduce jobs back then. I don't think they're using it on MapReduce anymore, but back then that was what it was designed for. So there's a lot of stuff that's kind of hard to express in SQL, although you might be able to do it with UDFs, but it's much more complicated in SQL. And then after Google published the paper in 2004, everybody in this world was like, whoa, there's this like great thing that Google is doing. And Google probably back then has the largest, maybe even now, has the largest scale in terms of infrastructure. If that's what they came up with, let's learn from them. So this whole team at Yahoo started doing this Hadoop project based on the ideas from GFS and MapReduce, and started Hadoop. And eventually open source Hadoop, I believe, in around like 2007. And in the beginning, there's two components in Hadoop. There's HDFS and Hadoop MapReduce. So HDFS is the storage part, modeled after GFS. And MapReduce is the compute part, modeled after MapReduce. Sometimes in this industry, when you talk about big data in terms of technology stack, Hadoop is essentially synonymous with big data. So that brings me to a little bit of history. I don't know how much you guys learn about history in here. There's these two guys, David DeWitt and Michael Stonebraker. They are two of the most well-known database researchers. Michael Stonebraker is actually a professor at Berkeley before the 2000s. He essentially started the Postgres project in Berkeley, along with other many things. He just won the Turing Award this year, actually. So David DeWitt is a guy from Wisconsin who has also done a lot of the foundational work in parallel database systems. So back in 2008, they jointly wrote a blog post, which you can no longer find, called MapReduce, a major step backwards. Essentially, the high-level idea is this MapReduce thing is really stupid. We at databases systems have done it all, and this is a strict subset and a much inferior implementation of databases. And he gave more reasons here that I'll come back. And this actually triggers sort of almost like a wall. People started publishing papers to demonstrate different points of views. There are papers that published from the basically DeWitt and Stonebraker camp at the most prestigious academic conferences about how bad MapReduce is based on benchmarks. And then the Google guys started countering. So Jeff Dean and Sanjay actually published another paper in the Communication of ACMs, refuting all the claims they were making. So it's actually a fairly interesting and dark chapter in sort of big data technology history. But we'll come back to this. But the real question is, why didn't Google just use databases if sort of MapReduce is strictly an inferior subset of databases? And I think we cover some of them, but I think just to give a more comprehensive sort of analysis of this, one is cost. If you remember the definition from Gartner, that whole paragraph, we took the 3 V's out of it, but the second part actually is information assets that demand cost-effective and innovative form. So there's a cost factor here. It's about economics. And So back then, even now, the way database vendors charge is actually by some data size per dollar. Or sometimes you might get one that charges you by the number of cores you're using in your system. So if Google, let's say if there was a database system that Google could have used and they needed to pay for support, it would actually be a very crazy number they have to pay because they have probably the most amount of data anybody could possibly imagine back then. So it simply, I think just from a cost point of view, would not make any economic sense for Google to be using a commercial database. The second part is about scale. There was no database systems back in 2003, 2004 that would demonstrate it to work at the petabyte scale. Even now, I think it's kind of hard to find referenceable cases of databases that would work at the petabyte scale. And then data model, we talked about Google has a lot of data like HTMLs, images. Those don't really fit very well in your relational form. And compute model, while you might be able to do a lot with SQL, SQL is sort of not enough because how are you going to write a SQL query to crawl the web? It's very hard. You might be able to do it through UDFs, but it's fairly hard to capture it in SQL. And last but not least, I'm tossing this one out. I do think part of it is also the not invented here syndrome that a lot of engineers suffer from this. So I myself included. Engineers like to build your own stuff. It's much more proud to have your own stuff. And I don't think this is probably a non-trivial factor also in there. Considering Jeff and Sanjay were not from database background. However, I think Stonebreaker, if you look at the points they were talking about, one part is a giant step backward in programming paradigm. What they were essentially referring to for MapReduce is the programmability. So it turned out MapReduce as a lower level framework is great. But if you're using MapReduce directly, it's actually fairly frustrating to use for a couple of different reasons. One is, actually the most important reason is for any real job other than word count, which is the hello world of big data. Any real application typically requires more than one MapReduce. So what ends up happening is usually we actually chain different MapReduces together. Like for example, your single query, a SQL query like a group by, you're probably breaking down into like 2 or 3 MapReduces. A Google indexing pipeline itself that indexes the web was 21 MapReduce steps. And then if you're running like iterative machine learning algorithms and all of that, they also get compiled down to many, many different MapReduce steps. And you guys only learn about Spark, but if you learn about the Hadoop MapReduce, how to program MapReduce, essentially each of the map functions is one class, along with like it's a bunch of imports. Each reduce function is another class, along with a bunch of imports. And each of them has a lot of setup you need to do. And if you want to connect 2 of them together, you need to instruct the first step to output data to a certain place, and the second step to read data in from that place. So there's a lot of spaghetti glue code, which makes the code actually much harder to understand. So with that, on the open source side, people started building higher level frameworks. And there are 2 frameworks that become fairly popular. The first one is Hive. I think back in maybe 2008, Facebook started doing this project called Hive. What Hive does is, instead of programming MapReduce now, you give it a SQL query, and it's going to compile the SQL query down into MapReduce jobs and run it on a cluster. And Pig is this thing done by Yahoo, actually by a Berkeley alum, Chris Austin, also back around the same time. What Pig does is it gives you a query language that's similar to SQL but not exactly the same. And what it does is also just compiles this query language into MapReduce jobs for execution on a cluster. And this tool essentially becomes the foundational high-level framework on top of MapReduce. And they were so successful that I think nowadays, if you look at all the Hadoop clusters, over 90% of the MapReduce jobs are actually not generated by writing MapReduce, but just by Hive. Pig, back then, was also very high, but there's a steady decline of Pig, and Hive is basically taking over. essentially nobody really writes MR jobs anymore. Everybody's just writing Hive. So what Hive does, again, it's fairly simple. There's a lot of different parts that you probably all learned about. There's a SQL parser that actually takes in a SQL query, processes it, constructs a syntax tree, has a query optimizer that picks how you actually construct a physical plan for execution. And the physical plan is essentially a bunch of MapReduce jobs that reads data from HDFS. So this is how Hive works. There's another problem with MapReduce that people are starting to realize when they're using it more and more. The first is programmability. They will talk about ease of use. So it's somewhat mitigated by the higher level framework. So now it's easier to write. The second part is performance. And the problem with it is essentially each MapReduce job is reading all the input from HDFS or disk. And after the map and reduce step, you will write all of them out to disk again. Now, if you have a single query that needs to actually have multiple map and reduce steps, for each of them, the intermediate data is essentially to write them to HDFS and read them back in immediately. And what this means is, remember, when you write data to HDFS, it gets replicated to 3 copies, and this might be a lot more expensive operation that happens in the background. So it's actually a fairly costly process. There's a lot of disk I/O and network I/O that's happening. And the second part is MapReduce is it's very restrictive. It's almost too restrictive to the point that there are other sort of higher level primitives that's actually lacking from that programming model. People are sort of finding very soon. Like one simple case is in a lot of workloads, sometimes you want to actually broadcast a data set. So for example, if you're running machine learning, you might be updating some model at every iteration. And once you finish updating that model, you want to broadcast that model to every single worker. So your nodes can actually know what's the latest model. And that is actually fairly hard to do with MapReduce. The way we do it is you write the model to HDFS, and then everybody reads from HDFS back in again. So it's kind of cumbersome and also slow. So now, this brought me to Spark, which you all experts now in. Back in 2009, Matei Zaharia started the Spark project as his PhD, part of his PhD work at Berkeley. And it was open source in 2010. The Spark was designed essentially to address both problems of MapReduce. One is programmability, and the second is performance. So instead of defining map and reduce classes, what Spark allows you, that you are all seeing, is actually you treat data. You sort of view the world as just transformation on data sets. So you have data sets, there are RDDs. And then there are functional transformations you apply on data set. For example, map and reduce are both just transformations on the data set. And then the sort of, initially it's only a Scala API, but now the Scala, Java, Python, and as of last night, R API for Spark. People soon discover that Spark is actually, it's a lot less boilerplate to write. So now if you have 10 steps of MR, you just write 10 map and reduce function, pass them closures. You don't need to define a million classes. And you don't need to define how you pass data from one MR step to another. It's just sort of data set transformations. And there's a couple other things that are kind of unique about Spark. One is you could, even on a cluster mode, you could do interactive analysis based on a command line REPL for Scala and Python. So this actually, it makes it much easier to develop and to do exploratory analysis on data. And the last part, which while your students when you're students you don't really care much about, but in practice, it's very important, is now you can actually unit test your Spark program because there's different modes you can use, which makes it much, I think, better for real-world deployments. In terms of performance, what Spark does is it generalizes the map and reduce into multiple stages of map reduce is chained together. What we call is like a DAG, basically a direct acyclic graph of tasks that's chained together in Spark. And and because of this DAG, now you could actually, Spark engine under the hood understands the output of the first map and reduce just goes to the second map. And now, instead of writing all the output to a disk, you could actually just stream through it, directly passing the output of the reduce to the next map. So now you cut out all the intermediate I/O, and then there's other primitives that Spark provides. For example, you could actually put the whole data set, the whole RDD in memory. And once you put it in memory, you can repeatedly query it without even going to disk at all for that. I think it's fairly common that you find like Spark programs, or well-written Spark programs at least, that outperforms the MapReduce variant somewhere between 10 and 100 times. So to show you programmability, I don't know if you guys I know you guys wrote Spark jobs. Have you ever written like an MR job? Anybody? 1, 2. 61C. Oh, I see. They were torturing you in there. So this is what Google's C++ API for MapReduce looks like. It's just taken straight from a Google paper. In reality, the Hadoop one's slightly more complicated than this because more imports you have to put. This is how we run word count. And it's kind of long. And as you all have seen, this is how we run word count in Spark in about 4 or 5 lines of code. If you use Java, it's going to be slightly longer. If you use Python, it's about the same. So it's actually resulting in much substantial improvement in programmability. The second part is performance. I don't have there are all kinds of random numbers to show in the past, but I think since I did this last year, it's pretty cool to show. So there was this benchmark called the sort benchmark. What it does is it asks you to sort 100 terabytes of data in a reliable fashion. So this is assuming machines could go down. And it doesn't matter how many machines you use, doesn't matter what you do. So there's a lot of companies that would build sort of sort machines. They might build custom hardware, they might build custom software to sort it. And it turned out last year's record, actually 2 years ago now, 2013 record was set by Yahoo using Hadoop. So what happened was, I was talking to the guys there, they had about 2,100 machines that were coming in as new machines. They haven't put into production use case yet. So basically the Hadoop team asked them, hey, can we use them? There's this benchmark. It's kind of going to be cool to show off our sort of technological advancements, how great we are. And give me a week, and I'm going to run this benchmark. So they ran it, and it becomes sort of the record of 2013. So 2,100 machines, sorting 100 terabyte, took about 72 minutes. So last year, I was kind of bored. Of course, it's not the case. I was trying to demonstrate so the performance of Spark. I was looking for benchmark to beat. And somebody just suggested, why don't you try to run the sort benchmark, see how fast you can sort. So I started doing it, and we actually, sort of throughout, in the course of running these benchmarks, we actually run into a lot of engineering problems with scalability that we had to fix, which was great feedback back to Spark development. But the final result was we actually ran it in about 200 machines on EC2 and took about 23 minutes to sort the same 100 terabyte. So this is a new record, or the latest world record right now. What we did is, so the machines are actually slightly newer. So these are 2014 EC2 machines versus like 2013 Yahoo machines. There are SSDs on this, so the I/O bandwidth is actually higher and all of that. But it was fairly exciting to actually see essentially what grew out of here, beating Hadoop by almost 30x on a per node basis. Last fun bit to add, this whole benchmark was started by another Turing Award winner called Jim Gray, who got his PhD from Berkeley. And because 100 terabytes is not a lot of data in 2014, we also went ahead and stored a petabyte on a similar sized cluster in about 4 hours. So Spark was designed initially to address two things, right? One is programmability, the other one is performance. And over time, we started seeing different frameworks and libraries on top of Spark that also gets developed. And now this essentially Spark SQL is a SQL engine on top of Spark. It's like Hive, except it's compiled on SQL to Spark. There's a streaming engine that's essentially for doing real-time analysis of data. So as your data is coming in, you want to make decisions directly. And there's a machine learning library, and there's a graph computation engine. And then as of last night, Spark R is merged into Spark. There's all this stuff. And this is actually fairly different from Hadoop in the sense that a lot of these libraries are actually fairly efficient on sitting on top of a general engine. So if you remember, MapReduce are horribly slow for a lot of things, and then they become much more efficient here. So in short, what Spark does is initially it focuses on performance and better programmability. And because of this too, people started developing higher level frameworks that actually make it now become what we call a unified engine. And what a unified engine means is you can do a lot of different things to satisfy your common data analysis. And if you can actually do all this in a single system, you no longer need to learn sort of a whole multiple different systems of doing different things. And the other fun part is Spark is now the most active open source actually software in the big data space and also in the data space. This is actually a highly unscientific comparison of popularity because I think Hadoop is probably actually still more popular in the sense of mentions and hits, but I don't know why Google Trends. So at least based on Google Trends, if you search for Apache Spark and Apache Hadoop, Spark is actually bypassing Hadoop as of, I think, early this year. So with Spark gaining popularity, we spend a lot of time actually trying to learn from our users. So a lot of Spark users, in the very beginning, back in like 2011 or 2012, in the early days of Spark, all the early users are like crazy scientists, Haskell programmers, Scala programmers back then. They're pretty hardcore. So these guys know what a monar and monar means. I don't even know what they mean. If you do, talk to me afterwards. And so slowly, Spark is taking over the Hadoop ecosystem. It's also becoming a part of a Hadoop ecosystem that a lot of Hadoop users are switching to Spark to replace the MapReduce workloads. And this set of Hadoop users understands what it meant. They came from MapReduce land. They understood what it meant to program a map and reduce. And they understood sort of the functional API. But as we're trying to push Spark to a broader audience, we're starting to run into some trouble. And what do I mean by broader audience? I'm referring to people that's maybe not familiar with Hadoop, hasn't taken 186, so they don't really know Spark. These are like data scientists, data engineers, statisticians, typical Python users, or your R users. To these guys, the functional API and the idea of like reduce by key is still kind of remote. It's going to take them a while to understand. So one example is this like a Spark program. I'm actually not going to, I used to ask people what this means, and I wait for them to put up their hands. Should I do that? I'm just going to tell you an answer. What this does is I think it just computes the average age of each department. So this is using the Spark Python API. You could write a similar program with the Java API or the Scala API. And what I will show later is something like this. So the second part is actually pretty self-evident on what happens. It's probably going to take you like about 5 seconds to understand. It's computing an average age, grouping by department. It's actually very similar to a SQL query. What we have learned is schema is actually kind of important to a lot of workloads. The MapReduce idea of only having key and value is somewhat restrictive and maybe too restrictive that in practice most data pipelines ended up having more proper schema that you actually write. And if you don't have a good way to express schema in your framework, people ended up writing stuff like that with a lot of tuples. Earlier this year, we started this effort called Data Frames in Spark. And what Data Frames does is it's essentially giving you, it's like RDD, but with schema. So you have a collection of data that's grouped into columns with names and data types. And then there's a whole sort of domain-specific language designed for the common data analysis task. Like, for example, you do sampling, you get the schema out of it. You can do like project, filter, aggregation, and join all of this. And it's added a lot of different APIs in different programming languages. And this is what the data frame gives you. So in a way, Spark, I think from its, in like 2010 and 2011, took the world from having this crazy MapReduce word count to a much more concise word count in like 3 or 4 lines. And now with data frames, we're trying to take the world from like above there for big data down to somewhere that's much more concise. And what data frames does is it's actually fairly, I think, very interesting in the context of this class. It is actually SQL under the hood. And what I meant by that is the way we design the data frame API is data frame sort of transformations, or the DSL, which essentially is constructing logical plan under the hood. And once it constructs a logical plan, it ran through the whole execution engine that's identical as Spark SQL. So in the case of SQL, what you would do is you have a SQL parser that parses the SQL query and constructs a logical plan and run through a query optimizer and all of that. In the case of data frames, you're basically programmably constructing the logical plan and then go through this whole optimization. And based on, this is like a one-slide summary of our experience with sort of working with a broader audience in Spark. One is SQL is actually have a huge comeback. It's wildly popular. As a matter of fact, 100% of our customers use SQL. Now, don't misread that. So when I was showing this to a friend, what he was saying was, oh, so SQL is the only thing your customers use. Now, that 100% of our customers using SQL doesn't mean 100% of the stuff where our customers use are SQL. So they also use a combination of, like, for example, I myself write SQL all the time, but I also write other programs. So don't misread that. But it's wildly popular. Schema is fairly useful beyond key value. Like, key value is way too restricted. A lot of data pipelines, even though in the beginning it might be starting with unstructured, semi-structured data, you might be parsing JSON and all of that. At some point, you start having more properly formed schema in your data pipeline. I think for like over 90% of the data pipeline, that's the case. Now, because still somewhere you might have unstructured data, you can't really drop the unstructured, semi-structured data support. You still need those. And the last part is actually the separation of logical versus physical plans. It's also very important for performance optimizations. Like, most of our users don't really want to think about how do you do this join, how do you do this scan, how do I employ indexes. Actually, just being able to more declaratively specify stuff like SQL in the data frame API was a hugely important feature of it. So return of SQL. In a way, you have, all of you probably heard of NoSQL at some point, maybe even watched the MongoDB video on YouTube. There was sort of a Silicon Valley hipster type that's saying SQL is so enterprisey in the 90s and it's outdated. But what's happening is there's actually a whole comeback of SQL. So this, I think, is published in 2003. Essentially, in the whole NoSQL, like Hadoop is one of the the frontier of NoSQL land, right? You're going to MapReduce and all of that. But it turned out, for all the Hadoop vendors, SQL is now the most important thing. So SQL is a huge comeback. And so through its initially Hive, and there's other projects, like, for example, Spark SQL. Even if you go back to Google, you would think this is where MapReduce was born. Maybe that's the one place you wouldn't see a lot of SQL. Google published this paper, I think in 2010, Dremel, which is about a new parallel database implementation they did internally. They essentially run SQL very fast. It's not on top of MapReduce. In the following year, they published another paper called Tenzing by a different group that's doing a SQL on MapReduce framework. And I think the next year, they actually have one of the coolest title of the paper, Processing a Trillion Cells per Mouse Click. What this paper is about is called PowerJoule. That's another SQL system they built for running aggregations at Google. So you can see, even within Google, where MapReduce was born, SQL is having a huge comeback. It doesn't mean MapReduce is gone, but there's a lot of workloads that are now done on SQL rather than that. And that absolutely resonates with the open source part, like Hadoop and all of this as well. And why SQL, right? It's almost everybody here can write SQL. If I write you a SQL statement, ask you to produce the same thing in MapReduce, it'd probably be fairly tough for you to write it on the spot. Even if you write it in Spark, it's probably going to take you a while. And the other part that's very important, which is probably often underlooked when you just come out of school, is SQL is essentially the common language for basically like enterprise software. So you might have a whole suite of tools that's using SQL, and they only talk SQL. So now if you want them to talk MapReduce, you basically have no way to get maybe 10 software that's been 10 or 20 years old to be updated to write them. And there's tons of software like this. If you Google, maybe you can rewrite everything. But for most enterprises or for most even technology companies, they don't have that resource to handle that. And last but not least, schema is actually fairly useful. Now, so then it was a question, which is SQL on this big data stack versus SQL on in databases, like parallel database systems. What's really different? If all the past 10 years, there's a huge comeback of SQL, and with the decline, basically, I told you, most of MapReduce jobs are generated by SQL. All our customers run SQL. So how is this different? What really happened in the last 10 or 12 years? I think there are, again, two perspectives that I sort of hinted on in the beginning. One is about data and a compute model, and the second is about fault tolerance. So if you look at traditional database systems, like be it on a single node system like MySQL or Postgres, or even the parallel versions like Teradata, your big Oracle machines and IBM machines, and all of that. What they do is they have a monolithic stack that have a storage, typically with a storage manager at the bottom, that manages how the database stores data. And then there's the execution engine. That's your physical execution operators. Like, for example, this is how you do a hash join. This is how you do an external sort. This is a physical execution engine. This is a SQL part on top that essentially compiles SQL into the physical execution engine. And then applications talk to the database through SQL. You dump data in through SQL. In some cases, you might have a bulk loading tool, but it's still primarily sort of gated by the database. The only way to get data in and out is through talking to the database. And then typically data are very structured and normalized in relational form. If you look at the big data stuff, what's happening now is this general storage, like for example HDFS, sometimes you might even use like S3 and all of these other things. This data parallel engine sitting on top of it, like Spark, MapReduce, and there's higher level frameworks on top of it. Now, at the storage layer, the only thing the storage expects is a bunch of bytes. It just expects files. So you could dump arbitrary things in it. It doesn't really care if your data is properly normalized or relational. You could dump a whole zip, sort of a zip of JSON or images that you don't have to care about the format. Just put it in. So there's a decoupling of storage and the whole upper layer compute. And on the second part is now, even for compute, there are different layers of doing compute. For example, you could program a Spark job directly. If you don't want to and prefer SQL, you could be writing SQL through it. So there's multiple different compute models happening now. And as a matter of fact, like DataFrame is a slightly different programming model again than SQL. And machine learning is, again, you have higher level abstractions that's different from what you would do in SQL. So now applications can choose a variety of different programming models. And then the application could also directly program against a lower level model. So this too is actually a fairly big difference between how the traditional database systems work versus the new sort of big data ecosystem. The big data ecosystem is a lot more open and flexible in the sense that you can dump whatever you want into it. You might have trouble reading it out, but you can dump whatever you want into it. And you can write and choose a variety of different programming frameworks and models. The world is not static, so database systems are starting to change, especially in the last year. So again, traditional databases, you have monolithic stack. storage is coupled with compute. The only way to talk to storage and to get data in and out is through SQL talking to the database. But basically, starting about last year, every single database vendor is starting to roll out what they call Hadoop support. And how do you support Hadoop? You would put, you would decouple actually your database storage from your database engine itself, and then allow the database engine to read directly from HDFS and all this general storage. So now you could dump data, you could bypass the database to dump data into Hadoop, and then using data like parallel database systems to actually read the data out. So somewhat, it is you're starting to see sort of decoupling of storage from compute for the traditional databases. And then the other thing that's very important is because what you put in Hadoop often has a lot of nested data because data is not properly normalized or relational. So all these databases are also adding pretty aggressively functionalities to actually read from like nested data, like JSON and other formats. So you see now this database camp that's going towards the big data camp, right? It's learning from it. The other perspective is fault tolerance. In the past, parallel database systems typically employ what we call the coarse-grained fault tolerance. What it means is if in the middle of a query execution, if a machine fails, you just fail the query. Or maybe you rerun it from the very beginning. This is the way of doing recovery. So it's very coarse-grained. And what MapReduce proposed is what you call it, as opposed to coarse-grained, a fine-grained recovery. And what fine-grained does is, if a machine failed, only fail the task that will execute it on the machine, and just rerun those tasks somewhere else, right? So you don't have to rerun the whole query. You only rerun a small subset of it. Now, what happens if you have multiple MapReduce stages? If you have multiple map and reduces, in the case of MapReduce, the intermediate data is returned to GFS or HDFS, which means they're replicated and they're reliable again. So if one machine fails, you just recover from that intermediate data that's replicated. It was very expensive, if you remember what I was saying in the beginning. It's a costly way of doing sort of chaining steps together, but it's very robust. So there's one interesting thing. Actually, back in 2008, Google did a sorting of a petabyte on their MapReduce system. And what they found was they were using about 48,000 hard drives to sort a petabyte of data. And if I remember correctly, it took about 6 hours to sort it. And there's one interesting tidbit, which is every time they ran the sort, in that span of, I think, 6 hours, at least one of the 48,000 hard drives would fail. So in cases like this, fine-grained fault tolerance is extremely important because, for example, you're sorting a petabyte, and you use coarse-grained fault tolerance, which means we run the whole thing when one thing fails. You will never complete your job because you're bound to have basically one hard drive that will fail. But the question is, how many people really, or how many organizations really have 48,000 hard drives, and let alone the need to store a petabyte of data, or even just process a petabyte of data? Like, what if all I have is 20 nodes, which is probably the median size of the Hadoop clusters nowadays deployed in real life, about 20 nodes. We're talking about all this massive scale. If you only have 20 nodes, and my query is pretty fast, it maybe uses like gigabytes or maybe even a terabyte of data, but it returns in about a minute. How important is this fault tolerance? So the idea in Spark is actually, Spark started with a fairly interesting idea, which is let's combine the two. And the idea is I will allow you to checkpoint when the data processing is long and expensive, but in most cases, let's just do rerun from the beginning. Or in the case of checkpoint, rerun from last checkpoint. And so when fault happens, you just go back to rerun. But when faults are rare, essentially never checkpoint. And then this means there's no cost of doing that checkpointing. But if faults are frequent, you employ checkpointing. And then you actually go back to the MR model, which is slower, but you could actually always complete. So this is actually, if you're really to sort of identify a nugget in Spark from like what's novel, this is probably, I think, the most interesting part is how Spark handles the fault tolerance beyond the sort of the programmability and performance part of it. And this is actually fairly, I think, a fairly novel part. So just to reiterate again, what's really different? Databases historically are more monolithic. You have couple storage and couple compute and all of that. And then you have the MapReduce and all this whole big data ecosystem. They have very layered approach. You have general storage, you have some general computation engine, you have specialized frameworks on top of them, but you're not bounded to any one of them. Although in the past year, databases are becoming more and more like the MapReduce one. They're becoming more layered and decoupled. But still, I think up until this point, the big data stack is still much more flexible than a database stack. In terms of fault tolerance, databases didn't really have the need because they only have sort of tens of nodes and queries run in like minutes. It's extremely rare something's going to fail. So databases were just employing the coarse-grained fault tolerance. And then the big data sort of stack was in the beginning doing very fine-grained fault tolerance, very expensive checkpointing. But frameworks like Spark is actually trying to combine both ways of handling fault tolerance from databases and big data. So in a way, the big data sort of ecosystem is now also going more towards the database. So now, I believe what we are seeing now is essentially a whole convergence. The world had a huge divergence that you have all this whole big data stack that's very different, done by different people from the database stack. But we're seeing a very clear trend that ideas from databases are sort of sinking into the big data stack. And so some of the ideas from big data stack is also sinking into databases. And they are just evolving closer and closer to each other. I think if next time somebody is asking you to pick a side between NoSQL and SQL or Hadoop big data and databases, just tell them to watch this presentation. All right. That's the end of my talk. Any questions you want? Thanks. I guess in your 186, you usually don't end up with asking questions. Any questions you want to ask? So you can ask me offline as well. Sure. Yeah.
You mentioned very early in the presentation that the Google file system was designed to deal with very large files. And most web pages that you're indexing that they might be caching aren't very large files. So what would be the very large file thing?
Yeah, actually, that's a very good point. So what happened is, when you're crawling the web, you don't write each HTML page out as a single file. You actually compress them and you write them out. Basically, each HTML becomes like one record. And then you have like the whole web as a giant file. Or maybe you have a subset of the web as a giant file. And the reason is really, I mean, in a way it's out of necessity, because if you store each HTML as a file, just think about how many HTML pages there are on the web. Just keeping track of that file metadata can probably itself be a big data problem. Yeah. Cool. Yes? Yeah. Yeah, so Yarn is this, so MapReduce is what you do for compute, and Yarn is this whole new third thing, essentially, now. So remember, Hadoop used to have HDFS and MapReduce, and now it's much more like HDFS and Yarn and MapReduce. And what Yarn does is, I think it's called Yet Another Resource Manager or something like that. What it does is people soon realize, and in the open source world, if MapReduce is the only thing you run it's a little bit hard to justify an expensive cluster. You might want to run more than one thing on it. Like that's not MapReduce. For example, you might want to run like stream processing. Maybe you want to serve your live traffic out of the same cluster running your Hadoop MapReduce jobs. So they built a whole sort of resource manager that's responsible for scheduling resources for different frameworks. So MapReduce would be a framework. Spark would be another framework. Now, they hasn't been very successful in the sense that nobody's really putting their live traffic together with their sort of big data traffic because typically you actually want somewhat of isolation to make sure your live traffic have a stronger SLA than your Hadoop one. So there's actually some challenges that's coming from, so preventing Yarn from becoming much more successful. Right now, based on what I've seen, the number of frameworks that actually run on Yarn is very small. In the beginning, they dreamed of having like thousands of different things that would be running on it, but now it's more like one or two. Right. I think free to go. Thanks.